When you ask most people why we have not returned to the moon in 50 years, they offer you the same answer NASA itself has given 1,000 times. It was too expensive. The space race was a Cold War spectacle, they say. A competition that ended when the Soviet Union fell. We went to the moon because we needed to prove something to our rivals. Once we proved it, the mission was complete. The funding dried up. The public lost interest. Case closed. It is the kind of answer that feels complete enough that you stop asking questions. But I want you to think about that answer for a moment, because it contains a fundamental contradiction that almost nobody has noticed. If going to the moon was truly just about beating the Soviet Union, then why did NASA keep planning to return? Why did the agency develop the space shuttle specifically to ferry materials to a lunar base? Why did it spend billions on a program called Constellation that was designed to land humans on the moon again? Why did every single president from Nixon to Obama, regardless of political affiliation, authorize new lunar missions that ultimately never launched? The contradiction is this. America kept saying it wanted to go back to the moon. America kept spending real money trying to figure out how to go back. And yet, somehow, America never went back. That is not the story of a goal that was abandoned. That is the story of a goal that became impossible. And the reasons why, the actual reasons, not the easy narrative ones, were discovered only in the last 20 years. Mostly in the last 5. What NASA discovered on the moon in that time fundamentally changed what it means to actually live there. In 1972, astronauts Eugene Cernan and Harrison Schmitt left the lunar surface for the final time, and nobody has walked on the moon since. But the moon never stopped being studied. Satellites began arriving in orbit around it in the late 1990s, each one carrying instruments more sophisticated than anything we had sent to the moon before. The Lunar Prospector, launched in 1998, carried a neutron spectrometer, essentially a device that could see through the lunar surface by measuring how hydrogen atoms responded to cosmic radiation. Scientists were searching for water ice in the lunar soil. It seemed like a long shot. The moon appeared. From every Apollo photograph and every rock brought back to Earth to be utterly dry, parched, hostile. But the Lunar Prospector found something unexpected. There were signals consistent with hydrogen, potentially lots of it, concentrated around the lunar poles, buried beneath the regolith. The data was ambiguous. It could mean water ice. It could mean something else entirely. For years, the discovery hung in that uncertainty. Then, in 2008, the Chandrayaan-1 spacecraft, launched by India, carried an instrument called the Moon Mineralogy Mapper. It was designed to study the composition of lunar minerals. Instead, it discovered something that should not have been there at all. The instrument detected absorption signatures, the distinctive fingerprint of hydroxyl and water molecules, all over the lunar surface, not just at the poles, everywhere. The moon apparently was wet, and scientists had no idea why. This is when the story fundamentally changes, because the implications of water on the moon are not simply about the moon. They are about whether humans can actually stay there. They are about whether a permanent lunar base could function. They are about cost, sustainability, and survival. Water on the moon could be a source of drinking water for astronauts. It could be processed to create fuel. It could provide radiation shielding. But water on the moon also meant that every assumption NASA had made about lunar habitability since 1972 was incomplete. Everything had to be re-examined. Everything had to be tested against this new reality. Could humans actually live on the moon? Or had we simply never tried long enough to find out what was actually killing us? The search for water on the moon changed everything about how we think about returning there. And it is a story told almost entirely through the eyes of people who were not supposed to be telling it. In 2024, we are finally understanding the full consequences of what was discovered across the last 2 decades, and the answers are stranger and more consequential than most people realize. What I want to explore here is not why we stopped going to the moon. It is what we learned about the moon that made going back far more complicated than simply refunding the Apollo program and trying again. The first layer of the problem seemed simple at first. Water had been found on the moon. The question was straightforward. How much was there? And where exactly could we get it? Lunar prospecting became a new branch of planetary science. Orbiting spacecraft mapped the moon with increasingly precise instruments. The Lunar Reconnaissance Orbiter, launched in 2009, carried a device called the Diviner Lunar Radiometer, which could measure the temperature of the lunar surface with extraordinary accuracy. What emerged was a map of water ice deposits concentrated at the lunar poles, regions so cold that water could remain frozen for billions of years. The coldest areas, trapped in permanently shadowed craters, reached temperatures below -230 degrees Fahrenheit. That is cold enough to preserve ice indefinitely. In 2010, NASA announced that ice deposits at the moon's south pole might contain enough water to support a permanent settlement. The estimate was staggering. If you gathered all the water ice believed to exist in the permanently shadowed craters of the lunar South Pole, you would have roughly 600 million metric tons of it. That is the equivalent of filling Lake Superior halfway, concentrated in one region, buried under lunar soil. For the first time since Apollo, the moon seemed genuinely habitable. Building a base there would still be extraordinarily difficult, but the fundamental resource problem seemed solvable. Water was there. We could reach it. We could use it. The path forward was technically daunting but conceptually clear. We just needed time, money, and engineering. Then, in the years after that announcement, NASA and other space agencies began trying to actually understand what it would take to extract that water and use it in practice. This is where everything became much more complicated, because finding water was not the same as finding useful water. The first complication came from understanding how that water was mixed into the lunar soil. It was not frozen lakes waiting to be pumped. It was hydrogen and oxygen molecules bound into the mineral structure of the regolith itself, scattered throughout the top layer of lunar dust. Extracting it would require heating the soil to thousands of degrees, processing it, separating the water from the minerals. Every process that could work in theory consumed enormous amounts of energy. Energy would have to be generated on the moon or transported there from Earth. And the energy requirements to extract water from the lunar regolith, according to detailed engineering studies, were far higher than anyone had initially assumed. You would need nuclear reactors, or massive solar arrays, or both. The cost was beginning to escalate in ways that undermined the original justification for going back to the moon in the first place. We were supposed to be able to live on the moon because the moon had water. But using that water might be so expensive that it would be cheaper to bring water from Earth. The elegant solution was becoming a problem again. Then in 2020, something else was discovered that changed the entire equation. A team of researchers analyzing data from the Stratospheric Observatory for Infrared Astronomy, a modified Boeing 747 that flies into the upper atmosphere to study infrared light from space, detected water on the moon in sunlit regions, not just at the poles. Across the entire lunar surface, even in places that receive direct sunlight, water molecules were present. This discovery seemed to contradict everything scientists thought they understood about lunar water. Water should not be stable in sunlight. It should be destroyed by solar radiation. The ultraviolet light from the sun should break water molecules apart, yet there it was. The presence of water in regions where water should not exist suggested that something in the lunar environment was actively creating water, or protecting it, or both. Suddenly, the problem was not just about finding water and extracting it. It was about understanding a process that scientists did not yet comprehend. The moon had become less like a known resource depot and more like an ecosystem with its own chemistry, a system that was creating and destroying water in ways that defied prediction. This is where the story becomes personal, and where an outsider made a discovery that even the experts had missed. Sarah Hay, a planetary scientist at the University of Manchester working in a lab in England with no direct connection to any space agency's lunar program, was reanalyzing data from multiple moon-orbiting instruments when she noticed something odd in late 2023. The patterns of water distribution across the lunar surface did not match the patterns that would be expected if water was simply frozen in place or bound permanently into minerals. Instead, the water seemed to move. It seemed to migrate. It concentrated in certain areas at certain times, then dispersed. She published her analysis in a small journal with limited circulation. NASA noticed it only months later when other scientists began referencing her work. Hay had identified a mechanism that the major space agencies had overlooked. The water on the moon was dynamic. It was responding to changes in solar radiation. During the lunar day, when sunlight struck the surface, water molecules were being created through a process called photochemistry. Essentially, solar radiation was interacting with oxygen-bearing minerals and hydrogen-rich particles to create new water molecules. During the lunar night, when temperatures plummeted below -280 degrees Fahrenheit, that water froze and accumulated in colder areas. Then the next lunar day came, and the process began again. The moon was not just home to ancient water ice, it was actively making water, which meant that accessing water on the moon was not about finding a static deposit. It was about understanding and eventually controlling a chemical cycle. This revelation collapsed the timeline of lunar return missions almost immediately. NASA had been planning to land humans on the moon by 2025 as part of the Artemis program. When the full implications of Hay's discovery became clear, that water on the moon was not a simple resource to extract but a complex system to understand and manage, The timeline extended. It is now scheduled for 2026 or 2027 at the earliest. The European Space Agency pushed back its own lunar timeline. The Chinese National Space Administration adjusted its plans. Every agency that wanted to establish a lunar base suddenly realized that they did not fully understand their target environment. They had to do more work. They had to send more missions. They had to gather more data. The simple dream of returning to the moon had been displaced by the harder reality of having to actually understand it first. But Hayes' discovery created yet another problem, one that nobody saw coming. If water on the moon was being actively created through photochemical reactions, that meant the lunar surface was far more chemically active than anyone had believed. The radiation that was creating water molecules was also doing other things. It was altering the properties of the soil. It was creating reactive compounds. It was potentially creating an environment that could be hostile to human habitation in ways that Apollo missions had never fully explored. The moon was no longer a dead, static, unchanging world. It was alive with chemical activity. The very radiation that made the moon a poor place for biology also made it a place where chemistry was constantly rewriting itself. Living there would not simply be about protection from radiation and temperature extremes. It would be about protection from an environment that was chemically unstable in ways that we were only beginning to understand. The deepest problem, the one that has quietly reshaped every lunar mission plan since 2023, is a problem about time itself. The Apollo astronauts spent days on the moon. A few of them stayed for nearly 3 days. That was a brief window. The moon is a place you visit, but establishing a permanent base means sending humans who would stay for months, maybe years. That means exposing them to the full lunar day-night cycle repeatedly. 14 days of sunlight, 14 days of darkness. During the sunlight, temperatures can reach 260 degrees Fahrenheit. During the darkness, they can plummet to minus 280 degrees. The equipment on the moon has to survive that cycle. The people on the moon have to survive it. And now we know that during that cycle, the entire chemical composition of the surface is shifting. Water is being created and destroyed. New compounds are forming and degrading. The very ground beneath a lunar habitat would be in constant flux. We never tested any equipment for that. We never trained any astronauts for that. We never fully understood what it means for humans to live in an environment where the basic chemistry is changing on a daily basis. That is what the last 50 years of robotic exploration discovered. That is what made coming back much harder than simply repeating what Apollo had accomplished. NASA's Artemis program is real. The first crewed lunar landing is scheduled for 2026 or 2027. The European Space Agency is planning the Lunar Gateway Station for 2030. The Chinese plan to establish an international lunar research base by the early 2030s. These timelines exist. These missions are funded. These plans are advancing. But they are advancing now with a completely different understanding of what the moon actually is. It is not a stable platform for exploration. It is an active, dynamic world where the environment itself is participating in chemistry that we are only beginning to comprehend. Living there is not a technical problem with a fixed solution. It is an adaptive problem. The more we learn, the more we realize we need to learn. I think often about what it must have felt like for the scientists who realized, somewhere between 2020 and 2023, that everything we thought we knew about lunar habitability was incomplete. Not wrong. Incomplete. That is somehow worse. It means you cannot simply apply the old knowledge to the new problem. You have to start rebuilding your entire model of what is possible. What comes next is not a return to the moon. It is an arrival at a place we have never actually been before. When humans step on the lunar surface in 2026 or 2027, they will be stepping onto a world that is chemically active in ways that nobody who walked there before has ever experienced. They will be collecting samples of material that is being created right now in real time through processes that scientists are still trying to fully understand. They will be testing equipment in an environment that is fundamentally unstable in new ways. They will be preparing for the permanent habitation of a world that we are only just beginning to see clearly. The question is no longer why we have not returned to the moon. The question that matters now is, are we ready for what the moon has become?